Section 1.2, using patterns. In this first example, we're going to construct what we call a difference table to predict the next term of the sequence. Before we do this example, let me share my screen and look at a couple of definitions here. The first definition is the word sequence. A sequence is an ordered list of numbers. The terms that are in that sequence, when we say terms, we mean the numbers in the sequence. So going back to our example, this is what we could call a sequence, and each of these are individual terms of the sequence. This is the first term, the second term, the third term, and so on. There's a very famous sequence that I just wanted to bring to your attention called the Fibonacci sequence. It's named after Fibonacci, who was an Italian mathematician from the 1100s, 1200s. I think possibly Indian mathematicians used it much earlier, but most people call it the Fibonacci sequence. It looks like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. How does that sequence work? It's a strange sequence. But once we are given the first two terms, to get each term after that, we simply add the two that came right before it. Let me say that again. Let's pretend someone just handed us the first two terms, 1 and then 1. Notice that every term after that is the sum of the two right before it. Notice how 1 plus 1 equals to 2. Notice how 1 plus 2 equals to 3. Notice how 2 plus 3 equals to 5. 3 plus 5 equals 8. 5 plus 8 equals 13, and so on. It's just a very famous sequence. It's a strange one. It's not an easy one necessarily. You kind of have to be given the first two terms to make a sequence like this go. Later on in the lecture today, we'll look at a similar type of example where we're given two terms and then we have to do something to get the rest. What do you think that next term here would be, by the way, right after the 34? Think about that. (21) plus 34 equals 55. So we would have a 55 right there. Another famous thing that I want to bring your attention to is called Pascal's triangle. This one is named after this French mathematician from the 1600s named Blaise Pascal. Pascal's triangle goes like this. You see ones along the outsides like that. So we just start by putting ones all in those spots. And then to find all the rest of the numbers, what we do is we add the two that are right above it. Just notice how 2 equals 1 plus 1 equals 2, right? Notice how 1 plus 2 equals 3. Notice how 2 plus 1 equals 3. Any number you want to pick, look at the 15 there. Notice how that's 5 plus 10. Any number that you want to pick in this pattern, look at the 21 right there. It's 15 plus 6. So we get all the rest of the numbers in the triangle by simply adding the two that are right above it. Okay, let me pick another one. Here's a 35 right there. The 15 plus 20 made that 35 right there. So what would be maybe right here? It would have to be 70, right? Because 35 plus 35. If we were to draw another line, it would be a 70 right there, and so on. So this can extend indefinitely forever. And it's just a famous pattern. It's not necessarily related to what else we're going to talk about in our lecture today, but it's just a famous pattern I wanted to bring your attention to, because throughout the semester, I might refer back to Pascal's triangle, because some things that we do in math just seem to randomly show up in Pascal's triangle. That will happen as the semester progresses. A couple of times I will say, look at these numbers that we just came up with. Notice how they came from one of the rows of Pascal's triangle. Okay, let's go back to our notes here, our lecture notes. And the first question says to construct a difference table to predict the next term of the sequence. Okay, again, we're starting fresh. This is not at all related to Pascal's triangle. This is not at all related to the Fibonacci sequence. We're going to learn something called a difference table. So how does a difference table work? Well, the idea is to find the next term in the pattern or in the sequence. Sometimes that's difficult to do. This is not an easy question. It's not like I'm just adding 5 every time or something like that. So sometimes this is a difficult thing to do. A difference table goes like this. And it's not going to work on every single sequence, but it works sometimes. If they're asking you to do it in the directions, it's probably going to work. So here's what we do in a difference table. We actually take a difference, that means subtract, right? I'm going to go 10 minus 10. 10 minus 10 equals 0. The next one, I'm going to go 12 minus 10, which equals to 2. 16 minus 12. Remember, difference means subtract. You take the term minus the one right before it. 16 minus 12 equals 4. 22 minus 16 equals 6. 30 minus 22 equals 8. So again, the idea is I'd like to find a pattern on the top row and figure out what comes next, but sometimes that's pretty hard. And sometimes doing what we just did here is helpful, because if you can't find a pattern on the top row, well, maybe you can find a pattern on the next row. I think most of you do see a pattern on the next row, and maybe you can figure out how we can use that pattern to get the top row pattern. Let's pretend we didn't understand the pattern yet. Well, I could always do it again. I could do 2 minus 0. I could do 4 minus 2. I could do 6 minus 4, and I could do 8 minus 6. And maybe you see a pattern now on this third row. If you don't see a pattern now on this third row, I don't know what to tell you. So the next number here would be 2, right? If we were working on that third row. If we were working on that third row, the next number would have to be 2, because it's all 2's, right? So if that was a 2 right there, in theory, what would go right there, right? Well, 2, 0, 2, 4, 6, 8. I would kind of expect a 10 to go right there, but that also fits because 10 minus 2 equals 8. It is called a difference table, right? 10 minus 8 equals 2, I guess is what I should say. 10 minus 8 equals 2. Or looking at it going to the right, I could say 8 plus 2 equals 10. Likewise, I could say 30 plus 10 equals 40, and I think 40 should be my answer right there. So I think that question mark should be a 40. But we can see that because, 40 minus 30 is how I would get that 10, or 40 minus 10 equals that 30. So we should definitely have a 40 right there. That's the next number in the pattern. Let's do another couple problems like this with difference tables. This was a fairly simple one. All the numbers were positive. We really only had to go down 2 more lines to get to a constant. Let's try another one. Construct a difference table to predict the next term of the sequence. Once again, the idea is that we would like to find the pattern on the top line right here. I would like to know what comes next. But that's not always easy. You can try it. Maybe some of you can figure out a pattern, but I think a lot of us are going to struggle with that. So this idea of a difference table is something that, again, this is helpful sometimes. I'm not telling you this process that we are doing here is going to work on every single sequence that you look at, but it's helpful in some cases. For the purposes of our class, when I ask you to make a difference table in the directions, of course, it is going to work then. But if you were just walking down the street someday and a gang of mathematicians stopped you in a dark alley and asked you to figure out what number comes next in the sequence, I can't promise you that a difference table is going to work. You could try it. I can't promise you it's going to work all the time. But it should work in this example. So 3 minus 2 equals 1. 7 minus 3 equals 4. Again, difference means subtract. I'm getting these numbers by subtracting. 7 take away 3 goes right there. 3 take away 2 goes right there. 19 take away 7 is about to go right here. 44 minus 19 is, I believe, 25. 87 minus 44 is 43. That's called a difference table, what we're making right here. And the idea is, okay, maybe I didn't see a pattern on the top row. Maybe I could figure out a pattern right here. And maybe some of you can already see a pattern. If you can, go ahead and figure out what would go next in the second row pattern, add it to 87, and you got your answer. I'm going to assume a lot of us cannot see a pattern right there, so let's make another line. 4 minus 1 is what should go here, right? 4 minus 1. 12 minus 4 is 8. 25 minus 12 is 13. 43 minus 25 is 18. I think a lot of you do see a pattern right now. If you do see a pattern right now, go ahead and put the next number in this pattern right here, add it to 43, you got that number, add it to 87, you got your answer. If you don't see a pattern right now, that's okay, make another line. What's 8 minus 3? 5. What's 13 minus 8? 5. What's 18 minus 13? 5. Okay, now we see a pattern for sure on the bottom there, right? So let's use this pattern that we all definitely see on the bottom to work our way up until we get to where we want, this question mark. Of course, the next number would be a 5 if I were to put another one. And so you got to figure out what would go here then. Okay. What number minus 18 would give me 5? Well, that's 23. But another easier way to think of that is just do 18 plus 5. 18 plus 5. I know it's called a difference table. When we go to the left, we're subtracting, right? And 19 minus 7 equals 12. But when you go to the right, you can think of it as adding, like 7 plus 12 equals 19. 18 plus 5 equals 23. In fact, 43 plus 23 is what I could put right here. What is 43 plus 23? That's 66. And so our final answer is going to be whatever 87 plus 66 is. 87 plus 66 is 153. Our final answer, what goes in place of that question mark, should be 153. Let's do one more. This next one I think will be probably the toughest one because mainly because negative numbers show up and a lot of people get a little confused with negative numbers, especially when you're trying to subtract with negative numbers and things like that. Construct a difference table to predict the next term of the sequence. I want you to think about, well, first of all, when you see this, if you see a pattern right now, and you already know what goes here, if you see a pattern with these numbers, then go ahead and just answer it. You're probably a genius if you see a pattern already. I don't. Okay. But if you don't see a pattern and the directions are telling us to make a difference table, let's do that. Think about what would go right there. I think a lot of people miss this. A lot of people miss this. Remember how I'm getting this number. I'm doing 17 minus -3. I'm not doing 17 minus 3. I'm doing 17 minus -3. Think about that. What is 17 minus -3? It's actually 20, and a lot of people might get that wrong. Why is it 20? Well, when we subtract a negative number, remember we're going 17 minus -3. When you minus a minus, you get a plus. Minus, minus right next to each other like that turns into a plus, so that's why we get 20. So be very careful when negative numbers start showing up. I mean, your calculator would tell you the same thing. 17 minus -3. Now, on a lot of calculators, there's a minus button for subtraction, and then there's a separate button that might make your number negative. I know not everyone's calculator looks like this, but I would say on most calculators, it's not the same button you're pushing. I'm going to press minus, get the subtraction there. Then I'm going to press um, -3 like that. It does equal 20. You can see that. But make sure you understand how to do that on your calculator if you're using your calculator to help you here. What's 28 minus 17? That's 11. What's 30 minus 28? 30 minus 28 is 2. 27 minus 30. That's actually a negative number, right? Because we're subtracting something that's bigger than what we started with. 27 minus 30, -3. 27 minus 27, of course, is 0, and 42 minus 27 is 15. Remember, the idea is to try to find a pattern on this second row now. If you do see a pattern on the second row, you can go ahead and put the next number that would show up in the second row pattern right here, and then 42 plus that would be our answer up here. I'm going to assume that most of us do not see a pattern. I don't really see a pattern right now in this row. So do it again. Make another row. Think very carefully about what's going to go right here. It's going to turn into a -9. We are doing 11 subtract 20. 11 minus 20 is -9. We're not doing 20 minus 11. We're doing 11 minus 20. Right here, we're doing 2 minus 11. That's another -9. Right here, I'm doing -3 minus 2. Be careful what's happening there. -3 subtract 2 turns into -5. If you're already at a -3 and you go take away 2 more, now you're even more in the negative. Think about what's going to happen here. 0 minus -3. It's very similar to what I said up here. If we're going to do 0 minus -3, that's the same actually as 0 plus 3. If you're putting that in your calculator, 0 minus -3. Okay, again, it's probably not the same button. You're not pressing your minus button twice. You probably have a separate button to make it negative. Not going to look exactly like mine for, necessarily, but some have like a plus minus thing right here, which is probably the button you're looking for. Some of them have a negative kind of like that, but those are not the same buttons. This is for if you're subtracting two numbers from each other, and this is to make a number negative. 0 minus -3 equals to 3. 15 minus 0 equals to 15. I'm going to assume that most of us, again, probably do not see a pattern right here. So Go again. The idea here on the difference table is keep going until you see a pattern and then work your way back up. Think about -9, take away -9. I'm going to tell you that's 0. On the calculator, it would look like that. -9 minus -9. Again, remember that minus a minus, that becomes a plus. That's really -9 plus 9 is why we're saying 0. Think about -5 subtract -9. That's going to be a +4. -5 subtract -9 is +4. Why is it +4? Because that minus a minus becomes a plus. It's really -5 plus 9. -5 plus 9 is why we get 4. Think about 3 minus -5. That's going to be an 8. Again, that minus a minus becomes a plus. 3 minus a -5 is the same as 3 plus 5. And then finally, 15 minus 3 equals 12. The idea is, do you see a pattern now? I think most of you probably do see a pattern now in this line. If not, do it one more time. Go 4 minus 0. Go 8 minus 4. Go 12 minus 8. Okay, now we see a pattern for sure. So think to yourself, what would come next in this bottom row and work your way all the way back up to here. Of course, a 4 would come next. So if we had a 4 there, what would go here? Think about that. That would have to be a 16, right? Because 16 minus 12 equals to 4. Or because 12 plus 4 equals 16. That's the easier way to do it. This would have to be 15 plus 16, right? 15 plus 16, I believe, is 31. But it has to be a 31 because 31 minus 15 also equals 16. But the easiest is just to add right here, 15 plus 16. The easiest is to add now 15 plus 31 to go here, right? So what's 15 plus 31? That should be 46. And then finally, 42 plus 46 is going to give us our final answer. 42 plus 46 is 88, and we are done. Sort of a long difference table. There's a lot of negative numbers showing up. That's a difficult problem for a lot of people. Let's move on to our next example. Use the given nth term formula to compute the first 5 terms of the sequence. Okay, so this is some new vocabulary, I believe, nth term formula. What do we mean by that? So we have a formula here. This is called an nth term formula right here. And what's happening is this is describing a sequence. This is describing a sequence. This is a formula or an equation that describes a sequence. Let's talk about what kind of sequence is it describing. So when we have a sequence, we're going to learn new notation here. We're going to call the first term of the sequence a sub 1. This is called a sub n. This formula says a sub n equals n to the third power minus 5. When we have a sequence, the first term of the sequence, we can refer to it as a sub 1. Again, this is brand new notation. I don't think we've ever talked about this yet. I'm putting a 1 in that spot right there, so I'm also going to put a 1 in that spot right there. Notice I just recopied the formula that we were given by replacing the n with 1. Why am I replacing the n with 1? Because I'm trying to find the first term of the sequence. Ultimately, we're going to find the first 5 terms of this sequence, but we're going to start with the first term. So everywhere you see an n, You put a 1 there. Okay. What is 1 to the power of 3? That means 1 times 1 times 1. 1 times 1 times 1 is still 1. That's not super exciting. 1 minus 5 is my answer here. So the first term of my sequence is -4. We are sort of building up a sequence here. It's different than the problems we just did. In the problems we just did, I was trying to find the next number in the sequence. I was trying to figure out a pattern and find the next number. It's not what we're doing in this question. We don't have to find a pattern. We're given a formula that describes everything we need to know. We're just trying to find the terms of the sequence. What's the second term of the sequence going to be? We call that a sub 2. So all we got to do is put a 2 in both of those spots. Everywhere you see an end, we're now going to replace it with 2. So this is going to be 2 to the power of 3, take away 5. What's 2 to the power of 3? That means 2 times 2 times 2. That means 8. 8 minus 5. What's the third term of my sequence going to be? Well, I'm going to put a 3 now in each of those spots. 3 to the power of 3, take away 5. That means 3 times 3 times 3. That means 27. Take away 5, 22. We're not finished yet. We have to find 2 more. They want us to find the first 5 terms of the sequence. But just so you understand what's happening, what would this sequence look like? The first term would be -4. The second term would be 3. The next term would be 22. What's the next term going to be? Well, let's go figure it out. The next term would be the fourth term. We call that a sub 4. We're going to get that by putting a 4 right there. 4 times 4 times 4 is 64. Take away 5 is 59. That means 59 would be the next term of the sequence. 59 is the fourth term of the sequence. What's the fifth term of the sequence? Let's put a 5 right there and see what happens. 5 to the third power minus 5. That's the fifth term of the sequence. What's 5 to the third power? That means 5 times 5 times 5. That's 125. Take away 5. So we found the first 5 terms of the sequence, right? Would come next. I don't know. We could figure it out if we want by putting a 6 right there. But that's not what they were asking us to do. They were asking us just to come up with these first 5 terms. This first term is called a sub 1. The second term of the sequence is called a sub 2. The third term, the fourth term, and the fifth term. If you needed the sixth term, you go put a 6 right there, and then you know what comes next. If you want the seventh term, go put a 7 right there, and you know what comes next. You could even find the 100th term right now without having to know the rest of them just by sticking a 100 right there. So it's very nice in a problem like this to have a formula, to have an nth term formula. You could go pick out any specific term of the sequence. I could find the 20th term right now, or the 30th, or the 40th, or the 85th. I could find whatever term I want by just plugging that number right there. We don't always have a formula, but it's very nice when we do have a formula. It makes it easy for us to compute the terms of the sequence. We're going to do another one like that in just a minute. But before we do that next example, in the next example, the concept of raising a number to the power of 0 is about to pop up. And a lot of people either don't know how to do that or they forgot how to do that. Let's talk about how we raise a number to the power of 0. Like what's the rule? What's the rule? Well, the rule is that basically anything to the power of 0 equals 1. That's the rule. Now, I said basically because we're we're not supposed to do 0 to the power of 0. When we do 0 to the power of 0, and it doesn't work. Okay? We're not allowed to do 0 to the power of 0. It's undefined. Sort of like how we're not supposed to divide by 0. So for some of you, just understanding that, or just being told the rule, anything to the power of 0 equals 1, some of you are good with that. You're like, okay, my teacher said anything to the power of 0 equals 1, so that's what I'm going to do. And I was like that. I remember when I was younger, if someone asked me, for example, what is 2 to the power of 0? I would get it right. I knew the answer was 1 because that's the rule my teacher said. That's the rule. But I never really knew why. And that bothered me. I never really understood. Like, it doesn't make a lot of sense off the top of your head why something to the power of 0 should equal to 1. But why does 2 to the power of 0 equal 1? 2 to the power of 0. By the way, on my calculator, this is how I get an exponent. It's different on each calculator, so that's something you're going to need to figure out. You can always Google, just take the name of your calculator and put it into Google and something about how do I do exponents, and there'll be videos that pop up to show you. But 2 to the power of 0 is what I just put, and it says 1, right? So your calculator knows the rule. 3 to the power of 0 equals 1. 12 to the power of 0. Anything to the power of 0 is going to equal 1. Unless you try 0 to the 0, then your calculator gets mad. 35 to the power of 0 equals 1. Everything to the power of 0 equals 1. And so it's just a rule. And when I was younger, I knew the answer because that's what the rule said. But it still bothered me because I didn't really understand why. It didn't seem very intuitive. Sort of thing where sometimes I would sort of toss and turn in the middle of the night and wake up in a cold sweat. And my wife would be like, Mr. Yarbrough, are you okay? And I would say, no, it's just that like 2 to the power of 0. I don't know why it equals to 1. And she'd be like, it's okay, just go back to sleep. And then I heard, like someone taught me a cool explanation as I got a little older. Someone taught me a cool explanation that I really like. So I'm going to show you this explanation first. Let's stick with like 2 to the power of 0, for example. If I were to do, let me actually start with like 2 to the power of 5. 2 to the power of 5 means 2 times 2 times 2 times 2 times 2. That's 32. What's 2 to the power of 4? That means 2 times 2 times 2 times 2. That's going to give you 16. What's 2 to the power of 3? 2 times 2 times 2, that's 8. Okay. What's 2 to the power of 2? That means 2 times 2. So this is not a big deal. This is like, okay, I already know this. I thought we were talking about 2 to the 0, but let's keep working our way down and see what happens. Of course, 2 to the power of 1 is just 2. Now you obviously see a pattern here. As I go up, I'm just multiplying by 2 again, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. But that means as I go down, I am dividing by 2, right? 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So when it came time for mathematicians to decide how are we going to define 2 to the power of 0, they said, let's just keep that pattern going. Divide by 2, divide by 2, divide by 2, divide by 2. Well, 2 divided by 2 would be 1. And there you go. And that's true not only for a base of 2, you could put any base here. I could put a base of 3 or 4 or 5 or whatever, and I'm multiplying by that base as I go up. But that means I'm dividing by that base as I go down, and I will always end up at 1 right there. And so mathematicians just wanted that pattern to continue. Another cool thing about this pattern is if we keep it going, the next logical power would be -1. And if I keep the pattern of divide by 2, 1 divided by 2 is 1/2. The next logical power here would be -2, and 1/2 divided by 2 is 1/4. And that's why you're going to notice in math, when you take something to a negative power, it usually results in a fraction. So again, I'm specifically just focusing on 2 to the power of 0, but this would be true for any number to the power of 0, as we saw on our calculator. Here's another example, another way to describe what we just saw, another way to describe why this rule is what it is. Some of you may have learned a rule like something like this in math at some point, and when you see that, we're supposed to subtract. When you see that, we're supposed to subtract those exponents right there. As long as the base is the same and we're dividing like that, we're supposed to subtract those exponents. That should look familiar to some of you. So this is another explanation of this. Let me take like 2 to the third over 2 to the third. What is 2 to the third over 2 to the third? Well, I mean, if I use this rule, what I just told you, it should be 2 to the 3 minus 3. If you believe that rule, or you've seen that rule before, then it's got to be 2 to the 3 minus 3. It's got to be 2 to the 0. So on the one hand, it has to be 2 to the 0. But on the other hand, when we have a fraction like this and the top and bottom are the same number, we know that fraction is always equal to 1. In fact, if I computed 2 to the third, 2 times 2 times 2 is 8, and 2 times 2 times 2 is 8, and 8 divided by 8 equals 1. We know when we see a fraction and that we have the same exact thing on the top and bottom, it's always 1. And so that's two valid ways of looking at this. And if they're both valid ways, they better be equal to each other, right? 2 to the 0 better equal to 1 because this is good math and this is good math. So those better be the same answer. So it's just a couple different ways of describing why 2 to the power of 0 equals 1. I just focused on 2 because I had to pick a base, but this is true for any base. Any base to the power of 0 is always going to be 1. I say all that just to go to our next example because that's going to pop up in our next example, and a lot of people get confused about that. For our next example, we're going to compute the first 5 terms of this sequence. Very similar to the example we did a few minutes ago. If I want to find the first term of this sequence, I know it's kind of an ugly one, but I'm just going to stick a 1 in those spots where I see an N. I'm going to stick a 1 right there. So that's why we did this whole thing about how do you do a power of 0. That's why I just did that last explanation because it pops up right here. So what is -3 to the power of 0? I hope you understand that it's 1 because I just told you that it's always going to be 1. When you take something to the power of 0, it's always going to be 1. So I think my first term should be 6, right? 1 plus 5. Now I still would like to talk about that though, because some people, when you go to, you say, well, I didn't get that when I put it on my calculator. I didn't get 1 right there when I put that on my calculator. We need those parentheses on our calculator. When you see parentheses in the formula, you better continue those parentheses on your calculator. So the way I'm doing it, I'm doing parentheses, -3, parentheses, and then I'm raising to the power of 0. That's definitely 1. If you did it without parentheses, I think you're going to get the wrong answer. Because if you do it without parentheses, what it's doing is it's actually taking 3 to the power of 0 first, which is 1, and then it's just sticking a negative in front of that answer. That's not what we want, though. We want it. We don't want 3 to the power of 0. We want negative 3 to the power of 0. We don't want 3 to the power of 0 and then just stick a negative in front of the answer. We actually want negative 3 to the power of 0. That's what these parentheses do. So we actually want to take negative 3 to the power of 0. You need to put it in with the parentheses. That's what I'm saying. And that's going to be true for the rest of this problem too. So I'm going to find the second term of the sequence by putting a 2 right there. Go ahead on your calculator if you need to do negative 3 to the power of 1. I doubt you need to because anything to the power of 1 is always itself. A to the power of 1 is always A, no matter what your base is. Okay, so negative 3 plus 5 is what I'm getting right here. Negative 3 plus 5 equals to 2. How am I going to find that third term of the sequence? We're just going to put a 3 right there. Put a 3 right there, put a 3 right there, do the math, you get your third term of the sequence. This means negative 3 to the power of 2. Negative 3 to the power of 2 means negative 3 times negative 3. Negative 3 times negative 3 is positive 9. Plus that 5 we got there. We should get a 14 here. Some of you are going to say, I didn't get a positive 9. Well, that's probably because you forgot your parentheses there. They gave us parentheses in the problem. We should continue those parentheses right there. Let's find the fourth term of the sequence. To find the fourth term of the sequence, I'm going to put a 4 right there. 4 minus 1, of course, is 3. What's negative 3 to the third power? It means negative 3 times negative 3 times negative 3. That's going to become a negative 27. Negative times negative times negative ends up negative. And negative 27 plus 5 is negative 22. They wanted us to find the first 5 terms of the sequence. So for the last part of this problem, we're going to put a 5 right there, and right there. 5 minus 1 is 4. This means negative 3 times negative 3 times negative 3 times negative 3 again. That's going to be a positive answer. Negative times negative times negative times negative is going to end up positive. Anytime you're doing a negative multiplied by itself an even number amount of times, you're going to get a positive answer right here. That should be an 81. If you do a negative raised to an odd power, that should be a negative answer right there. Okay. Negative raised to an even power, that should be a positive answer. Negative raised to an odd power, that should be a negative answer. So this is 81 plus 5, which of course is 86, and we just found the first 5 terms of that sequence. So again, the sequence, I mean, we're finished. Like this is the work. Like that's what they wanted us to do. But just to show you, the sequence would look like this. The sequence would go like 6, comma 2, comma 14, comma negative 22, comma 86. And what we're saying is this is called A sub 1. This is called A sub 2, and so on. So we're still working with sequences here. This is just different than what we had been doing earlier in the section and probably in the last section, where our main job was to find the next number in the pattern. That's not what we're doing here. It's not what we're doing right now. We're not trying to necessarily just find the next number in the pattern. We're working with a formula that was given to us, in this case, to compute the first 5 terms of the pattern. If you wanted the next term, what we would call a sub 6, you could easily get that by just putting a 6 right there and see what happens. Let me come back to one thing I said. I believe I was talking about it right here when I said I got a positive 9, but I bet you some of you got a negative 9. And that's because you probably didn't put the parentheses on your calculator. And some people say, well, why is that parentheses so important? Why does it make such a big difference? Well, here's why. Again, I'm just focusing on this little part right here and trying to explain why it's positive 9. If we do it with the parentheses, we're squaring a negative 3. We are literally going negative 3 times itself. And I think everyone knows negative times negative is positive. That's why we get a positive 9. But some people say, okay, I get that, but why doesn't the same thing happen here? Is the parentheses that big of a deal? Well, yeah, because what I'm squaring here is not negative 3. I'm squaring 3, and then I'm putting a negative in front of the answer. That's what this notation means. Because of the parentheses, the negative is carried along. It's along for the ride with the 3 the whole time, so negative 3 shows up in both spots. Without the parentheses, it's just 3 that's getting squared, and there's just a negative just kind of hanging out on its own in the front. But 3 times 3 is 9, and then you just stick a negative in front of it. That's why they're not the same. And this problem is not talking about this. This problem is talking about this. So be very careful. Anytime you're raising a negative number to a power, you need to carry along those parentheses. It's not as big of a deal if it was a positive base. You could get away with not having the parentheses and it'll still work. It'll still give you the right answer. But if you have a negative number that you're raising to a power, you better carry along those parentheses all the time. Okay, so again, my answers are these things, right? A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. That's what this question wanted me to compute. We're going to move on to our last example here. Our last example is, it's not the Fibonacci sequence, but you may remember what we started today with was I showed you something called the Fibonacci sequence. And I said, in the Fibonacci sequence, you have to be given the first 2 terms, and then we can do some math to get the rest of them. So sometimes there's a type of sequence where they just tell you the first 2 terms. Or say, look, we're just going to give you 2 numbers, and then we're going to start doing some math after that to find the rest of the terms. So what this example is saying is to find the third, fourth, and fifth terms of the sequence defined by a sub 1 equals to 3, a sub 2 equals to 7, and a sub n equals 2a sub n minus 1 plus a sub n minus 2 for n greater than or equal to 3. That's a lot of words, and a lot of people are confused right now, and that's okay. So let's go through this example and let's try to figure out what they're saying. They're asking me to find the third, fourth, and fifth terms of the sequence. They're not asking me to find the first and second terms of the sequence because they already gave that to us. It's right here. They already gave us the first and second terms of the sequence. That's why we don't need to find it. We just need to find the next few, right? So what's the first term of the sequence? It's 3. What's the second term of the sequence? It's 7. Right? I mean, if I were to draw out this sequence, 3 would come first and 7 would come next because that's what it says, right? So my a sub 1, my a sub 2, right? What's going to be my a sub 3? What's going to come next? What's the third term of the sequence? I don't know, but it says when you're trying to find a term of the sequence, but your base is bigger or equal to 3, then we got to use this formula here. Let me say that again. When you're trying to find any term of the sequence, when it's 3 or higher, when your base, the term you're trying to find, right? When your term you're trying to find is 3 or more, when n is greater than or equal to 3, now you got to use this formula. Okay, so this is where this formula is going to kick in. I don't need this formula for the first or second term because they just told us what it was. I need this formula for the third term and the fourth term and the fifth term and anything greater than or equal to the third term. That's what they're saying right here. So if I want to find a sub 3, I'm simply going to stick a 3. All right, it's weird, but I put a 3 right there, and I put a 3 right there. That's how I find a sub 3. That looks pretty strange, but let's just follow the math. What's 3 minus 1? 3 minus 1 is 2. What's 3 minus 2? 3 minus 2 is 1. So all I did was I put a 3 in those spots. I went ahead and did 3 minus 1, 3 minus 2. And then you look here, you say, well, 2 times a sub 2. What's a sub 2? I don't know what that means. Wait, what is a sub 2? Well, look over here. A sub 2 is actually 7. This is a 7 right here. I know what a sub 2 is because I was told that a few minutes ago. I also know what a sub 1 is because I was told that a few minutes ago. So a sub 2 got replaced with 7 because of what it says here. A sub 1 got replaced with 3 because of what it says here. 2 times 7 is 14. 14 plus 3 is 17. The third term of my sequence would be a 17. What would the fourth term of my sequence be? I don't know. But we gotta go follow this formula because 4 is greater than or equal to 3, so we gotta use this formula here. I'm going to stick a 4 in these spots. To find the fourth term of the sequence, I'm going to stick a 4 right here and right here. And then I'm going to do the math. 4 minus 1, 3. 4 minus 2, 2. Then I'm going to say, what is a sub 3? I don't know what a sub 3 is. Well, we actually do know what a sub 3 is. We just did that. A sub 3 turned out to be 17. So that's actually 17 right there, right? What's a sub 2? You say, I don't know what a sub 2 is. Yeah, you do. It's 7. Okay. All the stuff we need are gonna all the things that we need here is gonna we have already done them. They were either given to us or you just did it right here. So a sub 2, I'm gonna replace with the 7 right there. 2 times 17 is 34, and 34 plus 7, I believe, is 41. We just found the fourth term of the sequence. Would you like to find the fifth term of the sequence? Again, as I'm doing these lectures, I think it's always a good idea for you to pause the video and just try it before I do it and see if we come up with the same answer. I'm not going to pause because you can pause whenever you want. So I'm not going to stop. I'm just going to keep talking. But it'd be a good idea for you to go try to find the fifth term of the sequence right now on your own and then unpause it and see what we get together. So for that fifth term of the sequence, a sub 5, I'm going to put a 5 in those spots right there. I'm going to do 5 minus 1. 5 minus 1 is 4. I'm going to do 5 minus 2. 5 minus 2 is 3. We say, what does that mean by a sub 4? Well, we know what a sub 4 is because we know it's 41 because we did that work just a minute ago. So I know when they say a sub 4, they're referring to 41. So this is 2 times 41. I know when they say a sub 3, I know they're referring to 17 because we figured that out a few minutes ago, right? So I know that a sub 3 is actually a 17. I know 2 times 41 is 82. 82 plus 17 is 99. We just found the fifth term of the sequence, and that's what they wanted us to do, is find the third, fourth, and fifth. So that fifth term of the sequence is actually 99. That's called a sub 5. But again, this is my work, right? These are my answers here. This is the third, fourth, and fifth term of this pretty ugly sequence, which was defined very strangely, right? The way they defined it was we had to be given two terms to even start. I couldn't use this formula unless someone just said, hey, here's the first two terms. Now we use this formula from then on. From the third and higher is when we use this formula. We don't need this formula for the first two terms. They were given to us. We need this formula when your subscript is greater than or equal to 3. When that number is greater than or equal to 3, that's when this formula kicks in. That's what they mean. That is our last example. That will be the end of this lecture. See you next time.